In this video, we shall look at a few problems that show how conservation of linear momentum can be applied to collisions. Problem 1. A 4 kg block with speed 3 meters per second collides with an 8 kg block that has a speed of 2 meters per second moving in the same direction. After the collision, the 8 kg block moves in the same direction as before, but now with a speed of 2.5 meters per second. First, find the velocity of the 4 kg block immediately after collision. So let's sketch the initial and the final states. The initial state is where you have two blocks. So the first one is the 4 kg block. So this is 4 kg. And it's moving with 3 meters per second. And then you have another block which is 8 kg moving in the same direction with a speed of 2 meters per second. Now let's look at the final state, the state after collision. The 8 kg block, now it's moving in the same direction, but now with the speed of 2.5 meters per second. We are to find the velocity of that 4 kg block. Let's call this velocity v. Of course, this velocity v can be either to the right or to the left. That's what we want to figure out. So let's apply the principle of conservation of linear momentum that says the initial momentum of the system, that is, the linear momentum of the system before the collision, must be the same as the linear momentum of the system after the collision. Let's calculate the initial momentum of the system, the initial linear momentum of the system. So momentum of the 4 kg block is the mass m times the velocity. Now let's take the rightward direction to be represented by the unit vector I hat. So the velocity is 3I hat. This term right here is just mass times velocity. That's how we calculate linear momentum of an object. Now let's calculate the linear momentum of the second object, the 8 kg block, before collision. The mass is 8, the velocity is 2 meters per second to the right, so 2I hat. Now let's calculate the final linear momentum of the system. So you have to equate the initial linear momentum of the system to the final linear momentum of the system. The final linear momentum of the system is linear momentum of the 8 kg block plus the linear momentum of the 4 kg block after the collision. So for the 8 kg block, it is mass 8 kg times 2.5 I hat, because the 8 kg block is moving to the right. Now the momentum of the 4 kg block is the mass 4 times the unknown velocity that we are trying to find. When you solve for v, you get 2I hat. Of course, the unit is meter per second. So that is the velocity of the 4 kg block immediately after the collision. Now let's do part B. What is the change in total kinetic energy of the system due to the collision? So the change in kinetic energy of the system is given by the kinetic energy of the system after the collision minus the kinetic energy of the system before the collision. So let's calculate these two terms, Kf and Ki, separately. Kinetic energy of the system after the collision can be calculated from that figure. So it is the kinetic energy of the 4 kg block, so half m times the square of speed. Now the speed of the 4 kg block after collision is 2 meters per second, so the square of that is 4. Now the 8 kg block similarly is half, the mass is 8, the speed is 2.5, so square that. Now let's calculate the initial kinetic energy of the system. So that diagram right there, so half times the mass is 4 and the speed of that 4 kg block before the collision is 3 meters per second, so 3 squared, plus half times the mass of the 8 kg block is 8 kg and the speed prior to collision is 2 meters per second, so 2 squared. So you get the final kinetic energy to be 33 joules, and the initial kinetic energy turns out to be 34 joules. So that means the change in the kinetic energy of the system is 33 minus 34, so minus 1 joules. So there is a certain amount of energy lost during the collision. Such a collision in which the initial and final kinetic energies are not the same, or kinetic energy is not conserved, is called inelastic collisions. Problem 2. Two objects undergo a completely inelastic collision. These two objects are of the same mass and have the same initial speed. Note that they have the same initial speed, not velocity. After the collision, they move away together with the speed equals to half their initial speed. What is the angle between the initial velocities of the objects? So let's sketch initial and final states quite generally. So let's call this M and M. And they are moving in some ways like that. So we're dealing with motion in 2 dimensions because there is some kind of angle involved. Now note that the velocities are different, but the speeds are the same. So let's call the velocities of M, the first M, as u1, and the velocity of the second M as u2. Now because the speeds are the same, so the magnitude of the u1 vector is the same as the magnitude of the u2 vector. Now what is the final state? Final state, now we are dealing with completely inelastic collision. That means the two masses stick together after the collision and move together. So that means you have mass M and M stick together and move with some velocity. Let's call that velocity v1. However, we know the speed or the magnitude of this v1 is half of the magnitudes of u1 or u2. So say u1 or u2. We are told that they move together with a speed equals to half their initial speed. So these information are stated here and here in blue. Now let's apply conservation of linear momentum to the system. The initial linear momentum of the system in this state is mu1, that is the linear momentum of that m, plus momentum of this m, which is m times the vector u2. So this linear momentum of the system prior to collision must be the same as linear momentum of the system after the collision. After the collision, they move together, so the mass is 2 times m, and the velocity is v1. Now you see m cancels, like that, and you get this expression. Let's take the dot product of this equation with itself. So that means u1 plus u2 dotted u1 plus u2, and the right hand side is 2v1 dot into 2v1, so that is just 4 v1 magnitude squared. So let's do the dot product. u1 and u1, that is just the magnitude of u1 squared, u2 and u2, and that's going to give you the magnitude of u2 squared. The cross terms are this and that simply will be 2 u1 dotted into u2. But u1 dotted into u2 is u, the magnitude of u1, magnitude of u2, times cosine of the angle between them, and this is the angle that we're looking for. So let's apply these two results that we have already obtained earlier. So let's write the same line here as follows. So u1 squared, u2, is the same as u1. The magnitude of u2 is the same as the magnitude of u1. So that's u1 right there. Now this line here is just 2 times the magnitude of u1 squared. This times that, you get this. And don't forget cosine alpha. And that equals 4 magnitude of v1 squared. So equals 4. The magnitude of v1 is half of magnitude of vector u1. So square that is 1 over 4. The magnitude of u1 squared. So the 4's will cancel. So you see all the terms contains the magnitude of u1 squared. So that's can be divided out like that. So you get 1 plus 1 plus 2 cosine alpha equals 1. And you can solve for cosine alpha as minus half. That means alpha is 120 degrees. Meaning in our diagram here, that is that angle. And that is 120 degrees, and that is the angle between the initial velocities of the objects. Problem 3. Object 1 with mass m1, that is this, slides along a frictionless floor and collides elastically with object 2, that is this, which is at rest. So the speed of object 2 is 0 meter per second. The mass of object 2 is 4 times that of object 1. So that means m2 is 4 times m1. Prior to collision, the center of mass of the two-block system had a speed of 4 meters per second. What are the speeds of the object 2 after the collision and also the speeds of the center of mass after the collision? Let's first figure out u1. Now we know the center of mass of the system is moving at 4 meters per second prior to collision. So that means, prior to collision, the center of mass speed is 4 meters per second, and that's given by the mass m1 times u1 plus mass m2, the speed is 0, divide by m1 plus m2, which is in this case 5m1. m1 plus 4m1 is 5m1. So this is just 0, m1 cancels this m1, so you see that u1 is 20 meters per second. So that is the speed of object 1 prior to collision. So we can label the speed of m1 here, prior to collision, 20 meters per second. Let's apply principle of conservation of linear momentum. Momentum prior to collision is m1 times 20. I'm going to represent the positive speeds as representing the speed of velocities in this direction, the negative speeds belonging to velocities in that direction, equals the momentum after the collision is m1 times v1 plus m2 times v2. We know that m2 is 4 times m1, so we have an equation after the m1 cancels that says 20 equals to v1 plus 4 v2. So let's box this equation. This is a elastic collision, so kinetic energy is conserved. So the initial kinetic energy is the same as the final kinetic energy. So what is the initial kinetic energy? Is half times m1 times square of that speed, which is 400. Kinetic energy after the collision is half m1 v1 squared plus half m2. m2 is 4m1 v2 squared. m1 cancels like that, and you get another equation, which is 400 equals v1 squared plus a 4v2 squared. Of course, we multiply the entire equation by 2. From this equation, we see that v1 equals 20 minus 4v2. So substituting this v1 in here, we can get v2. And if you do that, you'll get the following for v2. 8 meters per second, and v1 is minus 12 meters per second. That means after the collision, m2 is moving this way, and m1 is moving that way. So this is the speed of object 2 after the collision. Speed of center of mass after collision is m1 v1 plus m2 v2 over m1 plus m2. You see that m2 is 4m1, so the denominator becomes 5m1. m1 goes away. Using these values for the v's, you get 4 meters per second. And that's the answer.